we need to study the properties of inversions. Yeah. So we need to apply our problem-solving strategies. Yeah. All right. Problem-solving strategies. All right. Yeah. First, the condition. It is known that these two elements, x2 and x7, are in place. So we need to consider how to, work on these two special elements. All right. Before we do the analysis, first we need to know a result, a simple result. So that is, under what situation? So here, the first thing we consider, because, the previous slide. Yeah. All right. Yeah. All right. So first, because in this question, we need to find the maximum number of inversions in this array. Yeah. And the given condition gives us some difficulty. So we need to consider the special role played by these two elements. Yeah. So in order to avoid that, so it's very common sometimes if something that makes things hard, first, we ignore it. So the first step, we ignore this condition first. So then the question is much easier to answer. So this follows, remember I mentioned that golden rule, problem-solving golden rule. We can modify the original problem to make it easier for us to solve. But that's our first round try, first round. Here, our first round, we do not consider the given condition x2, x7 in place. So let's ignore this condition. What is the maximum number of inversions? That's pretty easy, right? Yeah, because in that condition we know when the array is in descending order. Given array is in descending order. In this situation, it corresponds to the maximum number of inversions. Good. And you know how to calculate, right? The maximum. 2n minus 1. Maximum. Okay? Yeah. And with n equals 9. 9 elements. All right. Yeah. So we have this result. But next thing we need to consider x2, x7 in place. So we really need to dig into the details. What's the role played by these two in-place elements? Here, let me draw this line segment representing this whole array. So in this array, there are 9 positions, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 positions. But it is known x2, x7 in place. At the right place. After the array is sorted. Then we have freedom to arrange the remaining 7 elements. Then we need to find a way to make the number of inversions maximum. That's the goal. All right. Yeah. So now let's study. Yeah. Because when we talk about inversion, so here, let me recall the definition of inversion a little bit. Inversion. So we consider 2 elements, xi, xj, right? Yeah. Yeah. If xi less than xj, then the value of xi is greater than xj. Yeah. So the inversion we assume, here we assume I less than j. Yeah. All right. Yeah, but the value xi greater than xj. That's the inversion. All right. Now, let's look at the detailed information in our data. All right. Yeah. Detailed information. So we need to characterize the inversions. Yeah. Because we need to consider all the possible pairs. When we look at all the possible pairs, we need to count the number of inversions in all the possible pairs. So here we need to, remember, organize the data. Yeah, so here, another step in our problem solving. Organize the data. Organize the data. Yeah. We need to find a way to characterize our data. Use different categories. But in each category, we can count the number of inversions easily. But if we mix all the pairs from all the categories, very hard to count. Here, let's use this typical problem-solving approach. All right, the first category. First category. All right. Because here when we consider subscript I and j, so 2 and 7, yeah, because these 2 elements are special. So we need to separate these 2 elements out. Okay? These 2 elements and ij element, they do not have overlap. So the intersection of these 2 sets, empty set. So this is the empty set. That means the first category, we exclude, when we select arbitrary pair, we exclude x2 element and x7 element. Okay? When we exclude, that's our category number 1. Can you count what's the maximum inversions in first category? Do counting. All right? Yeah, that's first. Second one. All right. Jeff just joined us. All right. Second category. All right. We consider the pair. consider the pair x2, xj with j is not in 2 and 7. No. x2. No. First we pick x2 in the pair. The second element in the pair, we exclude x2, x7. Yeah. The remaining elements, remaining 7 elements, we pick as our second element in the pair. Then we do the counting. All right? Yeah. So that's the category number 2. Yeah. Then category number 3, yeah, consider x7 and xj. Yeah. So here the order x7, xj. Yeah. Yeah, let me do this way. Yeah, because when we consider x7 and xj, we do the natural order. Yeah, so here, yeah, because when I do this, you may understand there is the order question, right? x2 first, xj second, right? So here, let me use this way. This means we use the natural order. Natural order means the original order in the given array. Yeah, but here we do not want to discuss a few cases, so we just put there. All right, pick these 2 elements. Similarly, here we consider the natural order of x7 and xj with j different from 2 and 7. All right? Yeah. Category number 3. The last one. Yeah, because we want to cover all the pairs. Think about it. Yeah. We want to cover all the pairs. So there is one last case left. Last case is x2 and x7, right? Last. So now, all the pairs, we can divide it into these 4 categories. That's important. That's the way we organize the data. Very important. Okay? All right. So here, one concept. Let me talk about one concept. The way we do this kind of characterization, we call a partition. This is called a partition. Partition concept. What's the meaning of partition concept? Partition means when we divide the whole set of pairs, all the pairs, right? All possible pairs. All possible pairs we treat as a set. That is the original set. Then we want to divide it into 4 subsets. Okay? Subset. 1, 2, 3, 4. 4 subsets. Right? These 4 subsets should satisfy some conditions. So what condition? First, no overlap. These 4 subsets have no overlap, right? Yeah, no overlap. Based on our definition of these 4 subsets, no overlap. Okay? So no pair belongs to more than 1 subset. No overlap. And the second, these 4 subsets cover the whole set. We do not miss anyone. After we define these 4 subsets, then they cover all the pairs, right? Can you see that? All the pairs are included in one of the 4 subsets. Yeah. Another requirement, these subsets should be non-empty, but here, for our situation, we may release that condition, non-empty condition, because we do not require non-empty. If empty, one of the subsets is empty, then the counting number is 0, right? So we're fine with that. So partition has 3 different properties. So this partition, later, yeah. So here I review the concept in discrete math. In discrete math, we learned this concept, okay? The partition concept. So 3 properties. The first property, so no overlapping. No overlapping. Second property, cover the whole set. Whole set. Third one, each subset non-empty. Yeah. But for our situation here, we do not need it. Yeah, because it's not important for us. Okay? We do not need this number 3 property. Yeah. Because if it's empty, our counting number just is 0, right? So it's okay. So does not change our problem. No. All right. So based on this, then what do you need to do? Count the number of elements in each subset. And it's the maximum number of elements in each. Actually, number 4, the answer is obvious, right? Number 4, the counting number is 0 inversions, right? 0 inversion. Because x2 in place, x7 in place, we take this pair, no inversion, right? Yep. So these 2 numbers, when we consider them as a pair, no inversion. So number 4, 0 contribution to the counting number. So what you need to do is, how many inversions in subset number 1, how many inversions in subset number 2, and how many inversions in subset number 3. Then you add up these 3 numbers. That's your answer. Okay? Yeah. All right. And when you count, yeah, for example, when you count the number of maximum number of inversions, that result I mentioned, descending order, that can give you the answer for the first counting number. Okay? Second, third, then you need to consider, yeah. Second one, yeah, let me just use a few more minutes to do the second case. All right. Second case, x2 in place, right? x2 in place. So we consider all the pairs, 1, 3, 4, 5, 6. This in place, x7, right? Yeah. And 8, 9, right? But x7 we can remove it, right? Yeah. Because when we look at the subset number 2, we can ignore x7. Yeah, because that subset does not contain any pair containing x7. So They cross out temporarily. All right. Then, when we count the number of inversions, right, let's divide the elements into two parts. Element into two parts. For the element before x2, there is one element before x2. What is the maximum number of inversions when we count the first half? So, count max number of inversions in the first half. Because only one element, right? So you only have a chance to select one element. Then, together with x2, you count the number of inversions. So maximum number is 1, right? Because you do not have more than more than one inversions. The maximum number, so you only have 0 or 1. Yeah, because you may not have inversion. Or you have one inversion. So the maximum number for the part before this x2, that's 1. All right. Then, now you look at the part after x2. What is the when you count max number of inversions? After x2. So you pick one element after x2. Then together with x2 for all the possible cases, but you look at the maximum number of inversions. Think about that question. Because the only case when you select arbitrary of the remaining elements to give you inversion, that is x1 is in this part, right? Only x1. When you pick x1, after x2, you get one inversion, right? Other than x1, you can pick any other because the value of all other elements are greater than x2. So they won't give any inversions, right? Think about that. Yeah. So when you look at the part after x2, only when you place x1 in that part, you will get one inversion. Other than that, you cannot find any inversion. Yeah. So the answer for the second half also 1. Also 1. Okay? Also 1. So that is for subset number 2. I do this analysis. Subset number 3. Can you do similar analysis? Yeah. So using our thinking for subset number 2, you do the similar analysis. But because after x7 there are 2 elements. Before x7 there are 4 plus 2, 6, but we exclude x2, right? Yeah. So 5 elements before x7, yeah, yeah, and 2 elements after x7. Okay? Yeah, yeah. So you do the similar analysis to get your answer. Then you add up all these 3 numbers. Think about that. Okay? Yeah. All right. So the basic idea, quite clear here. Yeah. It is a little complicated, but here you can see we need a lot of knowledge pieces. We put them together to solve this problem. Although, so if you have other ways, that's okay. Here I just give you one way to solve this problem. Yeah. All right, so that's the hint part. Any other questions? You need my help? Yeah. So you can. This is our second chance, right? So before the deadline of homework assignment number 1. So this is the second chance. Any of you need my help on some of the questions in this assignment? Yeah. So you can let me know. Yeah. So I will find time. Yeah. So beginning of next class, or so I can record a video. Yeah. Because if I do in class, if I have time, I do in class, then it's much faster than recording a video after class. Yeah. So Zoom side, do you have a few more questions you want to ask me for help for this assignment? Anyone? If no, I just continue the lecture, all right? Yeah. Or before the end of class, you just let me know your questions. All right? Yeah. So let me go to the place we left last time. Yeah. Actually, the previous slide. Yeah. So let me just go back to the previous slide. Yeah. So this one. Okay? Yeah. Yeah. So let's recall the situation. All right. So the last time we solved this problem, but we consider the best case scenario. So what's the best case scenario? When n is power of 2, that's the easiest case. Because in that case, the floor function is gone. Yeah. When we call this function recursively, every time when we call it, we can remove the floor function immediately without any change. Yeah. So for that reason, that is the best case scenario. Then we find a formula. So the final formula we find. So this is the final formula. All right. This is the formula. All right? Yeah. So the next question, we want to generalize this formula to the general case. That's our goal. Yeah. So we apply the golden rule. Remember, we apply the golden rule. We modify the question. We consider the best case scenario, and we find a solution. But at the end, we need to go back to the original version of the question. So when we consider arbitrary positive integer n here, then we have a problem. Yeah. So here, when we consider the arbitrary positive number n here, then the question, can we still use the formula here? Yeah. The first question, if we want to see this formula still useful for the arbitrary case, the first thing we can see, we have a problem because the log base 2 function may not give us integer number. Log base 2 function in general, it's not integer number, right? But we know the capital A function, its function value must be an integer value, right? Capital A of n, it must an integer. So the left-hand side must be an integer, but this right-hand side may not be an integer. So there is, first we need to overcome this problem. Compatibility problem. Question, how do we fix this compatibility problem? We need to fix it. We need to do something to fix it. Okay? Yeah. And we want to apply some easy step to fix it. Not a complicated step. Easy step to fix the data type compatibility problem. All right? Yeah. So here, there are some easy way to fix the data type compatibility problem. We can take some integer function, right? Yeah. There are some function to make the non-integer expression to integer expression. Yeah. There are some convenient functions to convert a non-integer expression to integer expression. So that's something we can ask for help. So what's that? Two cases. The first case is the ceiling function. The log base 2 of n, we take ceiling function. The second case is floor function. Log base 2, I'll take floor function. These two functions can give us some easy way to make our non-integer expression to be an integer expression. All right. But the question is, which one do you want to pick? Do you want to pick ceiling function or floor function? No? So here, because what we are doing, we are making a guess, right? Yeah. So at this point, we are making a guess. But when we make a guess, we want to make a good guess, right? Yeah. Not a bad guess. We want to make a good guess. Yeah. So when we make a guess, we use our known information. The formula we derived for the best case scenario. All right. So now we need to make our decision in our guess. Okay? Is the ceiling function or the floor function, we can get a better guess. Yeah. Which one is a better guess? All right, the question. We do some testing, okay? To answer this question, we need to do some testing. Yeah. Because before we do testing, we do not know which one is better, right? So to answer this question, let's do some testing. So simple number testing when n equals 3. Okay? N equals 3. Yeah. Small number. Yeah. So we can get an answer quickly. All right? Yeah. When n equals 3, we know A of 3, number of bits, right? We write this 3 in the binary form. 3, decimal 3 equals 1, 1 in binary representation, right? Then there are two digits. 3 equals 1, 1, binary 2 expression. So the number of bits, 2. A of 3 is 2. All right. But if we plug in log base, so look at that. 1 plus log base 2 of 3, ceiling function will give us 2, right? Floor function will give us 1. So 1 plus 1, 1 plus 2. So 1 plus 2, we will get 3. But the 1 plus 1, the second case, we get 2. That means the floor function is a better guess. The floor function is a better guess. Okay? All right. Yeah. So, as a result, for the general case, yeah, so now our guess for the general case, it should be 1 plus floor function log base 2 of n. All right. But that's a guess. Okay? Yeah. Right. If it is correct or not, we need to verify it. We need to verify it. Yeah. The good thing is, if we have a good guess, then we have very good chance to verify if it is correct. Okay? Yeah. So there is a powerful method we can use to do the verification. That is the mathematical induction. Okay? Yeah. Mathematical induction. Mathematical induction requires that you need to have the result first. If you do not have the result, you cannot apply mathematical induction. Here, that result is our guess. So we have a guess, then we can apply mathematical induction to show this formula is correct. Okay? Yeah. It can be done, yeah, but here I want to skip it. Yeah. So I just give you the final answer. Yeah. Yeah. So it can be verified, yeah, by mathematical induction. This formula, 1 plus floor function of log base 2 of m, this number of bits is the answer of this question. Okay? Yeah. So try to learn the problem-solving strategies from this question. All right. Yeah. So we finished this topic. Next one. Yeah. B.2, variable size reduction. All right. So this time, another special type of size reduction, but a variable size reduction. Each round, the size reduction part could vary. Yeah. All right. So let's look at the problem number 10, greatest common divisor problem. Now, given two non-negative integers m and n, not both 0. All right. Find their greatest common divisor, GCD of m and n. Okay? Yeah. So this question. All right. Yeah. So for this question, here I'll give you the reference in the textbook. All right. Then, first, there is a known method to solve this problem in middle school. Okay? So in middle school, this method already given. Step 1, find the prime factorization of n. Yeah. In module 1, we talk about prime factorization, right? Yeah. So in module 1, we already know how to do the prime factorization. And we have an algorithm, right? Yeah, we have that, trial division, right? Yeah. So we have the pseudocode for that trial division. All right. So we apply prime factorization on first parameter n. Step 2, we apply prime factorization on second parameter n. Yeah. After that, yeah, remember, yeah, the form. Yeah, we use the standard form, right? Yeah. After we do the prime factorization, so we will take the standard form. So that's the prime power representation, right? Yeah. So we have a name for it. It's called prime power representation. Representation or form. Okay? Yeah. Yeah. So that, based on that standard form, we can find the greatest common divisor. Right? Yeah. So that's the, middle school method. find all the common prime factors from the standard form. So last step, compute the product of all the common prime factors. Yeah. All right. Yeah. And in this method, you can see the most important operation is this prime factorization operation. That's the most important operation. Okay? All right. Let me use a simple example to show this basic process. Find GCD of 60 and 24. All right. 60, let's apply the prime, that trial division algorithm, right? So we get a standard prime factorization form like this. 2 squared times 3 times 5. 24, the prime power form is 2 cubed times 3. Then we examine each prime number in the factor list. All right. So when we look at the power of 2, we get the greatest common prime factor 2 squared. When we look at the prime 3, we get a common prime factor 3. Yeah, so here. Yeah, I have 3. All right? So 5, no common factor, right? Yeah. So the product of these two prime factors, 2 squared times 3, we get a 12. Yeah. So this is the middle school method. Yeah. But the question, is this a good method? Is this a good method? Yeah. All right. The question is, when n and m are very large, yeah, so here we need to consider the case. Because in middle school, nobody considers large m and n case, right? Yeah, because you do not need to do prime factorization on large integers. Yeah, yeah, but when we look at this question again, we need to consider large input amount. So when m and n are very large, yeah, how large? You can imagine, very large. Okay, all right, very large. The prime factorization is, is extremely slow. Extremely slow. Okay? How slow it is. Yeah. Hard to imagine how slow. Even with the powerful computers we have today, still very slow. Still too slow. Okay? Yeah. So here I give you an example to give you some idea. Yeah. For example, so how large we can imagine thousands of digits, that large. That large. Each number has the number of digits, several thousands. Several thousands. That large. Imagine that. Yeah. So in that situation, yeah, so even you use a lot of computing power, large number of server machines, people can manage. Yeah, takes months, several months to complete the prime factorization. That hard. that hard. So you can imagine, we cannot rely on prime factorization operation. Too slow, extremely slow. Okay? For huge numbers, huge integer factorization numbers. Yeah. All right. So that's the reason we don't want to. So in the real world applications, we don't want to use this method. Yeah. So nobody wants to use this method in the real world applications. So we have to find a different and much faster algorithm to solve this problem. Okay, all right, yeah. So let's look at a different solution. So for this new solution, we apply our commonly used method. Reduce the problem size. To make it easier, how to reduce? We need to use recursion to do it. All right. So here, the most important mathematical tool we need to apply here is called a division algorithm. Yeah. We need some tool to help us reduce the problem size. Yeah. Here we pick division algorithm. What's that? Yeah. So very simple. Yeah. Everybody knows it. Integer division. Integer division. So here we put it in the algorithm. Okay. Given positive integer a and b, b not equal to 0, because we need to use b as the divisor. Divisor cannot be 0. Okay? All right. Then we have this conclusion. There exist unique integers q and r, q for quotient, r for remainder. Okay? Yeah. So the formula is r in the range greater or equal to 0, strictly less than b, and such that a can be represented as b times quotient number q plus remainder little r. That's obvious, right? So obvious. Yeah. So everybody knows it. But this simple method is very important in number theory. So it's a very basic algorithm. People call it division algorithm. So simple, yeah, but important. All right. Yeah. All right. So here, let's apply this division algorithm on our input. Two parameters, little m, little n. Yeah. All right. So we can apply it. Okay. All right. Yeah. And for convenience, we assume m greater or equal to n. Yeah. Yeah. If not, we just swap those two parameters, right? Yeah. So it's very easy to make m greater or equal to n. Yeah. So then we can apply division algorithm. Yeah. All right. So we have the formula like this. Okay. All right. Now we can do the size reduction transformation. So we need to do our formula transformation to show us the insight for size reduction. All right. So what kind of transformation? Related to GCD, greatest common divisor. All right. Yeah. So here, this is size reduction formula, but we want to understand this formula from this fraction. The left-hand side, we look at the fraction m over n. Left-hand side. Yeah. Then we apply division algorithm, right? So division algorithm here. replace little m by nq plus r, and after simplification, we have integer part q, little q, plus the fractional part little r over n. Yeah. So it's simple. Yeah. But from this expression, we can see the common divisor between m and n is the same as the common divisor between r and n. Because this q term, it does not impact that common divisor, right? Nothing to do. The q, integer part, has nothing to do with the common divisor, right? Yeah. It is separated. Yeah. Q term is separated from the fraction. So there is no relation for q with the common divisor, right? Yeah. So based on this observation, so these two fractions, we know these two fractions, they should have, yeah. So if you look at the common divisor between numerator and the denominator, the two pairs, the first fraction you have a pair of integers, second fraction you have pair of integers. These two pair of integers should have the same common divisor. Yeah. So that's the observation, the insight of size reduction. Okay? All right. So based on that, we derive this recurrence relation. This is recurrence relation. Yeah, actually, yeah. So this GCD, yeah. So we put there, but the NQ part does not impact the GCD, right? Yeah, because NQ is a multiple of m. Multiple of m has no impact on the common divisor. Yeah. So we can cross it out. So that's, we get this, we get a size reduction. GCD of n and r. GCD, yeah. So in this new expression, you can see the size is reduced. The data size is reduced. Okay? Yeah. So you can keep doing, because you can do next round size reduction, right? Keep doing next round until you need to stop at some place. When you can stop. When you can stop. Right? Yeah. Sooner or later, you need to stop somewhere. Yeah. When n is a multiple of r. Right? When n is a multiple of r, the GCD, you can see it immediately because it's r, right? The GCD is r, yeah? Because n is a multiple of r. So r is the greatest common divisor, yeah? So you can get an answer immediately, yeah? All right? Yeah. So now we are ready to write the recurrence relation. Yeah. All right. So next, yeah. So let us, based on this key, this is the key formula. Okay. So based on this key formula, let us derive our recurrence relation. Yeah. So it's the famous Euclid's algorithm. Yeah. So ancient, so more than 2,000 years old. Yeah. Very basic. Yeah. So very powerful algorithm. Yeah. The rule. Yeah. So our recursion rule. Right. GCD of two parameters, x and y, two parameters, yeah, equals there are three cases. Now, the first case, if y equals 0, x cannot be 0, right? Because our given condition, we do not allow both parameters to be 0. X cannot be 0. So if y equals 0, then x, the non-zero x, is the answer, is the value of the GCD function. No, because that's the greatest divisor. Okay? Yeah. All right. The second case, if x mod y, this percent sign modular operation. Yeah. We do integer division, but we only keep the remainder. We do not keep the quotient. We throw away the quotient. We keep the remainder. X mod y, if it equals 0, that means x is a multiple of y, then the answer of this function is y. Yeah. So the first two simple cases. Then case number 3, yeah, other than the first two simple cases, we have the main case. The third case is the main case. So we do size reduction. Now, so we swap the smaller, the second parameter. So we expect it is smaller. Yeah. Even if it's not smaller, it's not important, because the next round we will swap it to the first parameter. Okay? Yeah. So y comma x mod y. That's size reduction. Yeah. Here you can see when we apply the Euclid's algorithm, we don't need to do prime factorization. No prime factorization. We avoid it. So it is extremely time consuming. Yeah. Here we do integer division very fast. The modular operation very fast. Yeah. Okay? So in this way, we avoid the bottleneck, huge bottleneck, prime factorization, that bottleneck. So we can, make the GCD calculation much, much faster. All right, yeah. So that's the solution for this problem number 10. Yeah. All right, and then we finish part B. Yeah. Next, we will start part C. Yeah. All right, the topic, part C. Yeah. All right. Yeah. Here, one thing, because I mentioned this recursion. Yeah. So here you can see, to solve this problem, we need the power of recursion, right? Yeah. The power of recursion. And we cannot avoid recursion. So we know we need to use more resources, right? Yeah. More resource if we want to use recursion. Yeah. Yeah. But here, that's the cost we're willing to pay. Yeah. Because we want its result, its power to solve the relatively hard problem. Yeah. All right. Yeah. Yeah. C.1, Introduction to Fibonacci Numbers. Yeah. So in this part, so we will learn some more useful knowledge related to recursions. Yeah. All right. Problem number 11, calculate Fibonacci numbers. Yeah. Let's look at the recursion formula for Fibonacci numbers. Two base numbers, f0 equals 0, f1 equals 1. Then the recurrence formula, f sub n equals f sub n minus 1 plus f sub n minus 2 for n greater or equal to 2. A very simple recurrence relation. Yeah. Then, the goal, find the Fibonacci numbers f sub n. For any given integer n, what is the fastest way to calculate the Fibonacci numbers? Yeah. So in part C, let us study this topic. Yeah. Very simple, but very useful. All right. First, let's look at the first few Fibonacci numbers. Yeah. So based on this recurrence formula, we can easily generate the first few Fibonacci numbers. But when the input number, capital N, becomes larger and larger, so then the Fibonacci numbers grow very fast. Also, very large, much larger and larger. All right. Yeah. Our plan here. Yeah. So here, for this question, so there are two approaches. The first approach, we solve it algorithmically. We develop some algorithm to solve it. Yeah. All right. So write a computer program to implement some algorithm. Yeah. So that's the first approach. But there is another approach. Solve it mathematically. Yeah, because for this recurrence equation, there could be a mathematical solution. That is, people can find a math formula for this capital Fn. Some appropriate math formula. If you can find a math formula for the Fibonacci numbers, then you just evaluate that function in the formula. Okay? Yeah. So you do not need to, think computer algorithm to solve it. Yeah. All right. Two different approaches. Yeah. All right. Yeah. But you need to know how to derive a math formula. The equation looks so simple. Yeah. The equation looks simple. So there is a good chance to derive a math formula. Yeah. All right. Yeah. So for the algorithm way, recurrence relation is given. So the first idea, can we write a simple recursive function, this fiber of input parameter n, and the first two base cases, simple. The main case, return the expression of the recurrence relation. Fiber of n minus 1 plus fiber of n minus 2. How about that? Okay? So people can write a recursive function to calculate the Fibonacci numbers easily. As easy as this one. The question is this a good algorithm? How fast or how slow this algorithm is? How fast, how slow? Okay? Yeah. So the answer is surprising. The answer. Extremely slow. The answer is extremely slow. Yeah. So that's our project number 2 topic. So here, let me talk about our project number 2. Yeah. So we will experience how slow it is. Okay. We will compare a few different algorithms calculating the Fibonacci numbers. And how slow it is, here, let me use the asymptotic notations. We have learned asymptotic notations, right? Yeah. So here we can use that asymptotic notation to see how slow it is. All right. Using the asymptotic notation, big O of, so you know big meaning of big O, okay? Big O of phi of n, okay? What is this phi? Phi, golden ratio. Golden ratio, phi equals 1 plus root of 5 over 2, 1.618. Okay? Yeah. So we will study golden ratio in our next topic. Yeah. We will study golden ratio. Yeah. So 1.6 something. Yeah. Then it's exponential function. Phi to the n. It's an exponential function. We know exponential function grows much faster comparing with the polynomial functions. Extremely slow. Yeah. When you do experiments, you will see so slow. Okay? Yeah. Why it is so slow? Yeah. The first question we need to answer here. Why this algorithm is so slow? All right. Yeah. So, look, it is correct, no problem. But the main problem is it is too slow. It's not acceptable. So this slow, exponential function, slow, not acceptable in any application. No. Any application, if you see the algorithm is exponentially slow, nobody wants to take it. Yeah. All right. So next, we want to improve. Yeah, because we want to find a much better one. How to improve it? Greatly improve it. Yeah. All right. So next, we will work on that part. Yeah. Before we try to improve it, we need to know why it is so slow. No. Only when you understand the reason why it is so slow, you can find the right way to improve it. Otherwise, you don't know how to improve it. Okay? How to improve it? You do not know. Okay? Yeah. So let's want to find the reason. Here, I want to draw a recursion tree. In order to see how does the computer algorithm calculate the Fibonacci numbers, we need to draw a recursion tree. Here, I draw a relatively small recursion tree. So I start. So I want to calculate Fibo of 6, a small Fibonacci number. Okay? Yeah, very small. But inside computer implementation, inside the main memory, we use stack, right? Yeah, we'll push into the stack and do the calculation. So this Fibo of 6 is unknown, so we push it into the stack, and we need to split. We need to know the two values before we can calculate Fibo of 6. We need to know Fibo of 5 and Fibo of 4 before we can calculate Fibo of 6. But Fibo of 5 and Fibo of 4 also unknown, so we need to do another round splitting, 4 and 3, another round splitting, Fibo of 3 and 2, and so on. Keep splitting until we know the Fibo numbers. So that's the whole tree. After we reach the bottom of the tree, we get a value of Fibo of 1 and a Fibo of 0. We have the base cases, 2 base cases. So we can stop. Then we can go backward. bottom up. Yeah, we can do the calculation bottom up approach. At the end, we can find a Fibo of 6. Yeah. So that's the typical process inside computer memory for the implementation. Yeah. From this tree, you can see the problem, right? Yeah. So why it is so slow? After you look at this tree, I think most of you can see the problem quickly, yeah. Right? Because you have too much redundant calculation. Yeah. For example, Fibo of 2. How many times we need to calculate the Fibo of 2, right? So, you know, so many times. And that's only when we calculate Fibo of 6. Think about if we need to calculate Fibo of 100. How much redundant computation do you need? Think about that. Yeah, so not acceptable. That's why you get exponential slow algorithm because your tree grows too fast. You know, too much redundant calculation. Yeah. So after you know the reason, do you have an idea how to fix it? Our goal, we want to fix it. We want to eliminate all the redundant calculation. So our next task to do, we want to eliminate all the redundant. If you find a nice way to eliminate all the redundant computation, it's extremely fast. You will see. The problem is fixed. Extremely fast. Right? Yeah. All right. Let's take a 10-minute break. After you come back in the second half, let's look at the very powerful computer algorithm we can apply to fix this redundancy problem.